電磁波兵器から身を守る方法。
Done is I put a few pieces of Polish ham, lunch, in the same frame, and we're going to see what the microwave, which was designed to cook ham, does to it. So you can see it did a number on the ham, and again, only a very small fraction of the energy was absorbed by this thin layer of ham. It's crunchy, but it's good. All right, so now let's see if we can protect ourselves. Remember, water does absorb microwave energy, even though this is the long wavelength and it penetrates deeply into a wet medium. If we take a couple of wet towels, a thickness of moist towels that I just soaked in the sink, and we put this in front, we're going to see if it affects the ability of this to drive the microwave, to drive the fluorescent tube. So we'll turn it on. Let's see what happens. Now remember, when I hold this in front, it fluoresces. And as I move this away from the source, you can see that it works out to about, almost 2 meters here. It's pretty far. But if I place the water barrier in front, like this, no fluorescence. If I start this up first, and then block it, you'll see that the energy cuts out about halfway as far away. Again, all the way out to about here. All the way out to about here. Probably 2 meters almost. But if I place this water barrier here, and then try to drop the tube, it goes out in about 1 meter. Now you can see the light fluorescing. Watch what happens when I drop the metal in the way. Turns it right off, turns it on. Very effective. And we can see when I put this in front how much farther laterally the radiation goes. This is working as a deflector, not just blocking the radiation and protecting my parts, but sending the radiation laterally. Okay, next. This is the old hacked door from the microwave that I got this from. That's why they put these metal screens in the door. The door itself is made out of plastic and wouldn't block the microwaves from getting out. But these perforated screens allow you to see through them, but at the same time, they block the radiation. So what we're going to do now is try a perforated metal screen like this. I've applied this screen to our riot shield. And this has a couple of advantages. First of all, you can see through it. You retain the protection of the riot screen, but also protect yourself from the microwave. So let me show you how this works. Now this is where I get a little daring, okay? This is the fluorescent tube, and it clearly glows. But if I take this screen and I put it in front of the beam like this, I'm standing in the microwave beam, and it's protecting me. But not here. Here, but not here. And I feel fine. Now you can see that it glows, and you can see that it still glows. The wood does not block the radiation. Alternative to cardboard. And if we make the tube glow like this and place this in the beam, it doesn't do anything. Now, if we replace that with a very heavy piece of fiberglass, This material is so strong, it's an epoxy fiberglass composite, that it will stop a number of different calibers of bullet. But you can see that it doesn't stop the microwaves. See that we get the glow, and we also get the glow. As you can see, the Kevlar does not block the radiation. Tow carbon fiber cloth. The reason they call it ribbon tow is they've flattened out the individual little yarns in order to make the material extremely thin and decrease the sort of zigzag of the fibers. This makes this material extremely stiff and extremely strong, and is often used in aerospace applications and very high-end sporting equipment. The bottom line, though, is it's carbon fiber, and even though it's only 250 microns thick, it's electrically conductive. So let's see what happens. Now, as you can see, the beam in front, but nothing in back. In front, but nothing in back. And in fact, nothing over here, but you can see it's reflecting over there. And that's because this is an electrically conductive medium. This material is graphite film. It's also 250 microns thick, and it's formed from hydrostatically pressed graphite. It's often used as a heat spreader in electronic equipment, as well as high temperature gaskets in furnaces. It's also an excellent material for exfoliating graphene, as we'll show you in a future video. But the bottom line is this stuff is inexpensive, it's very flexible, it's soft, and it's electrically conductive. Now, once again, it glows, but it doesn't. It glows, but it doesn't. And as you can see, it reflects the energy, the space blanket or a thermal blanket, as a means of protecting ourselves. It'd be wonderful because it's nice and light, portable, and inexpensive. Question is, does it work? Now, this material is based on an extremely thin layer of a polyester film, great insulator, very strong plastic, on top of which they've placed a chemically vapor deposited layer of a few atoms of aluminum. And as a result, the material is electrically conductive. Now, if you look at the meter right now, this shows you when you've got electrical conductivity. If I touch these two probes to the surface, you can see that it's electrically conductive. However, if I turn the surface upside down and we do the same test on the back side, it's not electrically conductive. So the aluminum coating is placed only on one surface. So we're going to turn it back over like this. Once again, just to prove it, we have electrical conductivity. And what I'm going to do is I'm going to label this side front. We have microwaves in front, but nothing in back. In front, nothing in back. In front, it's getting down through the table, but not behind the barrier. And you can see that it effectively reflects the energy because of the angle of the panel. So this stuff really works. And what's nice is it's light, it's inexpensive, you can carry this around in a pocket. You feel the burning or you detect that you've got microwave radiation hitting you, all you have to do is take this stuff out, wrap yourself up like a hot pocket, and you're good to go. Maybe. Let me show you something. Now another option is to use a more robust material than the very lightweight space blankets, and that's to use an electrically conductive cloth. They're made in a variety of different formats, but basically what they consist of is an embedded mesh of a conductive wire, in this case very fine copper wires that are embedded in a plastic cloth. The spacing between the fibers is down around 50 microns, so they will stop extremely high frequency, extremely short wavelength radiation. In addition, this stuff is launderable, it's sewable, you can sew it, and it's nice and strong. So let's see if this material will block the radiation. Let's see if it blocks the radiation. A lot of intensity here, nothing here. It also reflects the energy a little bit on this side, not much, but a great deal over here because of the angle that we've got this panel set at.